guys remind me, because we've got a couple of clips of videos in here, to turn off the recorder so that it doesn't crash again. Okay, so we are working on more naming of enzymes today, regulation of enzymes, factor affecting enzymes activity, turnover number, and enzyme inhibition. That's what we're going over today. I will get that lab for you. Yeah, I did not copy it. That's 1110. Why is it so low I can't move it forward? This might be a fun day. Okay, so remember in naming of enzymes, we went over this a little bit last time, but if it ends in ACE, you've got an enzyme, and the first part tells you what you're cutting apart. So maltose, maltase, sucrose, sucrase, lactose, lactase, okay, and that's if it's just doing a specific thing. This is the common names, okay. If we want to be more specific, then we put in there what's happening to it, like hydrolysis and whatever. Remember that the in ones were what? If it ended in IN, what did that have to do with in your body? Digestion. Okay, so those are the key words there. And I don't know, oh, it is working now. Good. You want me to go back when my board's not working? Okay. Whoops, there. Let me see if I can get this other thing working. I don't know. It went away. And I don't know where the other thing is that I don't know where my other tool is. Okay, we are okay to go forward now? Okay, so nomenclature and classification of the enzymes. Three important aspects of the naming process. We sort of went through that before. We changed the ending to ACE. The in tells me it's something in the digestive system. Okay, that's the first one, so looking at the suffix. Second one is a type of reaction. So that's the first, usually put in front of the ACE or the in. And then what are we doing? What thing are we doing it to? And that's put as a name before the 1 and 2. So glucose oxidase, meaning it's an enzyme, it's oxidizing glucose, right? And we went over this last time, so that shouldn't be too hard. Sometimes you can't recognize the substrate by the name itself. So urease and lactase usually are hydrolysis reactions, but they're not told that they're hydrolysis. Does that make sense? So there's some that you just need to know by memorization, and those are two, are hydrolysis. Okay, so basic naming again. Substrate, if it's an alcohol, ethyl alcohol, whatever, type of reaction, dehydration, removal of hydrogen. Common name, alcohol dehydrogenation plus the ACE. So this right here is my enzyme. Okay. Systematic name, it just gives another one here. Has two parts. First, the name of the substrate. The second part is the reaction and catalyzed, but put in by the ACE. So lactate dehydrogenase. Okay, let's see what we can do here. Maltose. Maltase. Lactose. Lactase. Protein. They're a little bit different. This is in your notes, so you should be putting it in, I hope. Starch. Amylase, so it's not starchase. Okay, lipids. Lipase. Polypeptides. Okay, remember we also have the pepsin and trypsin that don't have the ACE, so that there's some that we just have to know. Okay, and some of them are easy to get the enzyme, but some are not so easy. So you need to know what they are. How far? This one? So I guess I won't be standing up for this one because my board's not being happy today. Sorry, guys.
At least you'll be able to sit down.
Yeah, I might fall asleep. Wake me up if I do. That would be bad. I've got to make it to that doctor's appointment. Okay. Okay, so here we go with all the ACEs again. And then we need to worry about how temperature affects the activity. We're going to be doing labs with this too. So things that affect enzyme activities. We first have to worry about temperature. And you will have a graph that goes like this at optimal temperature, and all of a sudden you get too high and your enzyme dies. This is why they worry about temperatures on infants and people getting too high, because once it gets too high, you kill the enzymes. You denature the enzymes. They don't come back. So that's why people die when their temperature gets too hot. It's a reacting force to try and to denature invaders in the body, but if it gets too high, it also denatures good things.
Does every human have like a certain amount of enzymes?
Oh. Mm-hmm. Yeah, you make your enzymes.
But you just said it.
Right, but if you get too hot, they die. You can't replace them fast enough. You die.
You can't replace them fast.
You die.
You just meant like you can't replace them.
So, for instance, if your pancreas dies, that's where your enzymes are made. You die. You can't live without your enzyme making thing, which is your pancreas. Okay? Yes.
Well, that's what burning flesh is, right?
Yep, that's what burning flesh is, Max. You should know this. You've been denatured. Okay, so there is an optimal temperature, and that's when we hit the top of the curve. Okay, and that's when things happen. All right. The other thing that we need to worry about is pH. So it will have an optimal pH. So if, for instance, when kids go off to college and they go to try and get into a sorority and they decide that they have to drink so much, their pH goes off this chart, and what happens is your enzymes stop. And you're actually killing yourself with alcohol. Okay? We have a very small range that things work in. And we get out of that range, and our body has 3 or 4 buffer systems that try and keep it within that range. And if you break those buffers, life is no longer. Okay? So, but each of these different enzymes has a different pH that it works with. So what was pepsin? Where is it found? Digestive. Look, but there's also trypsin that's in the digestive. Look at the optimal pH for both of these. They're totally different. The optimal pH for pepsin is 2, which is probably going to be in your stomach, right? Optimal pH for trypsin is just a little bit basic. Where do you think it's going to be found? Anywhere but the stomach. Okay, it'll be found in the digestive. The smaller, large intestines are in the mouth. Okay, so we have to be watching where things happen, and of course, carbonic anhydrase, that's in the rest of the body, where we're right about the 7 for optimal. No. It's included inside the digestive system. You don't want it outside the digestive system. If this got outside the digestive system, then you kill enzymes around that. So anytime you have a puncture in a bowel, it's a big problem, because it's letting all those acid and base things that were contained now out into your system that can't handle it. Okay, so let's go forward. So we just went through this. I just put it down here. Trypsin functions best at 8. Pepsin functions best at 2. These are digestive enzymes. They're exceptions to the rule. And the third thing that we need to worry about is concentration, substrate concentration. There becomes a point that no more reactions can take place. So think of it this way. If I have 10 girls and I have 40 boys and I'm going to marry them off, there becomes a point where I can't marry any more off if I'm doing 1-to-1, right? So it becomes a stalemate. I can only make 10 couples. That's as much as I can make. So that's sort of what happens with the point of saturation. You know, if I have one boy and I have all these girls, I can't, yeah, it just doesn't work. Okay, so enzyme activity will increase to a certain substrate concentration, and thereafter it remains equal or constant. So it's a boy meet girl kind of thing. All right, so then we go on to enzyme activity. This is the rate at which an enzyme will catalyze a reaction. So how fast can it get a reaction to go forth? If I call a matchmaker, how fast can they find me a match? So fast that I want. Maybe not so fast. Okay, and then we've got the turnover number, and that is the number of molecules of substrate acted on by one molecule of enzyme per minute. So basically, that's how many can I have a reaction with in 1 minute. How many reactions with the enzyme catalyze in 1 minute? Okay, and then we've got enzyme international unit, which is called IU, and that's a quantity of enzyme that catalyzes the conversion of 1 micromole of substrate per minute under specified conditions. So we get a little bit more specific. Yes? Pepsin? Pepto-Bismol is with bismuth. I don't think it has the peptide in it. No, it doesn't. Okay, so here are some turnover numbers. This number is how it would be demonstrated. So if we have papin, which is the hydrolysis of a peptide bond, the turnover number is 10 per second. So it moves pretty fast. Look at this one down here. Catalase will decompose hydrogen peroxide to hydrogen and water, hydrogen and oxygen, or try that again, water and oxygen, 10 to the 7th times per second. Yeah, it's like crazy amounts of times. Most enzymes turn over 10 to 1,000 molecules per second. That's a lot. That's a lot of work being done by an enzyme. You can get your homework done up. That would be awesome. Okay, so enzyme concentration, rate of reaction, enzyme concentration. Because enzymes are not consumed in the reaction, they can catalyze over and over and over again. Okay, the cell usually keeps the number of enzymes low. Okay, think of it if you were working on a job and you want to get as much work out of each worker bee as you can, because you don't want to have to pay a whole bunch of worker bees. You want to make some profit. So the same kind of thing here. They don't want to put much energy out. They want to retain that energy. So they keep the enzyme numbers low compared to the number of substrate. That's the things you're trying to break apart or put together. This is efficient. The cell avoids paying the energy costs of synthesizing and maintaining a large workforce of energy molecules. Okay, so here we go with enzyme inhibitors. When we work with an enzyme inhibitor, this is when we stop production. We don't want it to go forward. Okay, it will decrease the activity. A non-specific would be like a denaturing, or like spraying Lysol over a table to kill the bugs that are in the room. I'm not specifying I just want to kill the E. coli and not the staph bugs. I want to kill all of them. So that would be a denaturing. Okay, the specific, I can be irreversible, like denaturing, okay, or it can be reversible. In the body, we want it to be reversible because if I want to stop production of something right now, I might want to change it and turn it on. So we want an on and off switch. Okay, we have two different versions of reversible, competitive and non-competitive, with allosteric feedback, and we'll talk about each of these. First of all, in irreversible inhibition. If I'm going to irreversibly inhibit an enzyme, they're like suicide substrates. So they go in and sort of lock down where all the substrates would come in and into a enzyme and have the reaction go. They're suicide ones that go in and just stay there. They don't come out. They bind. They bind like a normal substrate to begin with, but they can't complete the reaction, so they get stuck in the site. Okay, so that's irreversible. Some others are called poisons. Okay, for example, any heavy metal, cadmium, lead, mercury, is known as an irreversible inhibitor because it's retained in the body and lost extremely slowly. Cyanide is a poison that prevents the activity of the cytochrome C oxidase and the enzyme in the electron transport chain in a cell. Therefore, it inhibits ATP production and cell respiration, so you can't breathe. That's why you turn blue when you have cyanide poisoning. You have blue lips and you have sort of a grayish blue appearance when they come and take you to the morgue. Okay? When we have a reversible inhibitor, what usually will happen is I put something in there that can come out. So one of them would be like a competitive inhibitor. It blocks part of the site so the substrate can't come in. We also have a non-competitive inhibitor, and that's like this one right here, where it attaches to something other place of the enzyme, and it changes the shape of the enzyme, so now the substrate doesn't fit. Okay, so you have two different ones, competitive and non-competitive, that you're going to be worried about with reversible. Just think competitive, it's going to go in the same place. Non-competitive, it's somewhere else, but it changes the shape of where the substrate would go. Okay? And this is some examples. So inhibitor substrates compete for active sites. Penicillin blocks enzyme bacteria used to build cell walls of bacteria. Antabuse treats chronic alcoholism. It blocks the breakdown of alcohol. And it works for severe hangovers and vomiting 5 to 10 minutes after drinking. Overcome by an increased substrate concentration. Saturated solutions with substrates so it can outcompete the inhibitor for the active site. That's how you overcome a blocking. So here's another picture again of a non-competitive inhibitor. It hits somewhere else on the enzyme, changes the shape of what the substrate would be, so or the accepting of the substrate, so the substrate can't come in. A competitive will go in to part of that site and block the substrate from coming in. Okay, so over-the-counter ACE inhibitors in your Seeger-Slaybaugh book, 20.1. I want you to go to there really quickly. We're going to talk about these 5 things I want you to pull out of that. So stop the video for a second. Okay, let's go through this. What is hypertension? High blood pressure. What is an octapeptide? Say it's an amino acid string. Okay. What does angiotensin do? Okay, and what is ACE? And what does ACE inhibitors do? Block it, right? Okay, so as we're looking at this, we've got a nice little picture here. This is dilated, this is contracted. This is a normal artery. What happens when it's dilated and contracted? An ACE inhibitor comes in and opens a coronary artery valve or arteries by blocking the receptor that would make it contract. Okay? All right, so let's do regulation now. We're on to regulation of enzymes. Catalytic behavior can be regulated. A cell containing thousands of different molecules that can react in many different ways. We've got to have somebody be the controller. A cell controls how many different ways they are allowed to react. In other words, they have rules. Okay, so I'm going to sometimes they need to turn off enzyme production because bodies can't handle too much of something, right? So regulation of an enzyme acidity within a cell is necessary for many reasons. Here's 2 specific situations. A cell that continues to produce large amounts of an enzyme for which the substrate concentration is always very low is wasting energy. the production of the enzyme needs to be turned off. In other words, if I don't have enough things, in other words, I had 2 people on the line and only 1 chocolate was coming through every minute, I only need 1 person there. I don't need 2. Okay, so if I've got too much though going on, if the production of the enzyme catalyzed is, I have making too much, it's wasting my energy too, because I don't know what to do with all this stuff and I need to turn off the production. So if I end up with a whole bunch of wood that has been cut and know what place to put it, not a good thing. Or too many dumbbells that nobody's going to be using. So we regulate it. So the big thing is we don't want to waste energy. Bodies are made not to waste energy, so we need to make sure we do not waste the energy. We okay to go forward? Okay, so binding molecules control whether an enzyme is activated or inhibited. I think of it like an on and off switch. Okay, they may change shape of the active site, so that would be a competitive or non-competitive? Non-competitive. Or they go into the active site, which would be competitive. Okay, one mechanism of allosteric regulation is feedback. So this is another way we can do it. So allosteric activation, the active site becomes available to the substrate when a regulatory molecule binds to the enzyme. So if it's bound to it, then it will allow things to happen. Allosteric deactivation is when the site becomes unavailable to substrate by a regulatory molecule binding to a different site. So we now can't do anything with it. So let's talk about these. Allosteric enzymes have quaternary structures composed of 2 or more chains. They have 2 kinds of binding sites, those for the substrate and those for the regulators. Their active and regulatory binding sites are distinct from each other and both in location and shape. So they're the different parts of the enzyme. Okay, often the regulatory site is on one protein chain and the active site is on the other, because remember it's going to be a quaternary structure composed of at least 2 chains. And then the binding of the molecules at the regulatory site causes changes in the overall 3-dimension structure of the enzyme. So, yes? Okay? I know, sorry. Okay, so then we have modulators, and modulators are substances that bind to the enzymes at a location other than the active site and can alter the catalytic activity of the site. So maybe I just want to, instead of having on or off, I just need to turn it down a little bit or ramp it up a little bit. So it's not a total on and off. Allosteric enzymes are when we have an enzyme with a quaternary structure whose activity is changed by the bonding of modulators. Activator again will activate it, increase the activity. And then we get to the feedback inhibition. And this is a process that's put into a lot of the systems in your body. When too much something is produced, it actually comes back up the road like and hits again to the site of the, my brain is not working, like a line of, I need this end product to come back up and finish this. Well, it gets to the point where I've got too much coming back up front, and so it'll shut down the line for a while. Okay, so let's look at it. It's sort of like this. This is what I'm trying to explain. So you have this line going on, and you need these enzymes, and then when you get to D, you have to have this come back up and feed here. Well, if too much of this comes back, this negative feedback, I got too much coming here, and so it will shut this down because I made too much of D, and there's not all of it being used. So that's what feedback inhibition is. The product inhibits this enzyme right here. Okay, and that shows you in a couple different ways how it's more visual right here. Okay. So then we get to more of the regulation of enzyme activity, the activation of zymogens and proenzymes. So here we go. As we go down here, you can sort of see the enzyme and the little trypsin going on back and forth, and enzyme activity. So we go a little bit farther here. The activation of zygomines. These are proenzyme or proenzymes are inactive before enzymes. Yes, thank you. Say it again for me. Precursors. Thank you. Like I said, my brain and my tongue are not connected today. So before I get to an enzyme, these are precursors to them. So some enzymes in their active form would degrade the internal structure of the cell. These enzymes are synthesized and stored as inactive precursors, and then when the enzyme is needed, the zygomin is released and activated where it is needed. Okay, so these are the things that move it on, and then when we finally get to where we want to be activated, right here, we get an active enzyme, which is a little bit different. It's almost an enzyme, but not quite. So some examples of zygomins. We've got a zygomin here, and then we've got the active enzyme. We've got a zygomin here, we've got an active enzyme. So we can go back and forth and back and forth and back and forth and back and forth. Okay. Activation usually requires the cleavage of one or more of the peptide bonds. The digestive enzymes pepsin, trypsin, and chymotrypsin are, as well as enzymes involved in blood clotting, are activated this way. So whenever I need, like thrombin, prothrombin will go to the site, and then thrombin, by being activated, will start clotting blood. So here we've got covalent modification of enzymes happening. And here, the activity of the enzymes may be increased or decreased by covalent modification. It means either addition of a group to the enzyme proteins, or by a covalent bond, or the removal of the group by the cleaving of covalent bonds. Phosphorylation and basically adding a phosphorus group or phosphate group, or taking one away, are covalent modifications. They are considered an on-off switch for an enzyme. So if I add one or take one away, I'm doing the on-off switch. These processes are governed by other enzymes, protein kinases and phosphatases, for the phosphate group. So going from ADP to ATP. Antibiotics also can bind to substrates or enzymes and cause enzymes to stop working. So antibiotics that inhibit enzyme activity, an antibiotic will kill a bacteria or inhibit their growth. Sulfa drugs are what was considered the first antibiotics. And so here we have a basic structure of a sulfonamide. So you have the sulfur group and the amide group and an amine group. And we get several other modifications here that can go on the R group. But these were to inhibit, they would bind to an enzyme and stop from reproduction. So then we get to chemistry in your health. When we talk about enzymes and diseases, what are inborn errors of metabolism? This is where we have problems with defective enzymes, where we don't have enzymes that are working like they're supposed to. It can be from a genetic, it can be from errors in and around things. There's a whole bunch of here listed: the sickle cell disease, cystic fibrosis, Tay-Sachs disease, the phenylketonuria is known as PKU, glycogen storage diseases where you can't store fat, maple syrup urine disease where your urine smells like maple syrup. Okay, a lot of different things. Oh, you would be if you had it. Okay, so I'm going to pause this. Okay, so we could do that with each of them if we wanted to, and go through the different diseases and that are found. But for every enzyme that we have, our body needs a coenzyme or an enzyme to break it down. So we've got several different things that we can work here with. A lot of people talk about vitamins. Vitamins are your cofactor to your coenzyme that will get a reaction going. Okay? So if you would open up your books to page 667, and I want you to look at avoiding mercury in fish, and I want you to just skim through it. I want you to look and see what you find. I just want to come back together and talk about this really quickly. It's something that's very hot in the news right now. Can be very harmful. Okay? So mercury's in fish. The ones that are low in mercury, the ones that are medium, and the ones that are high. What do you notice about the ones that are high? Yes? Mm-hmm. And omega-3 fish.
And so, does the amount of omega-6 that you need, like, would you need to eat more fish to get the correct amount of omega-6, but due to the restrictions, shouldn't?
See, that's the quandary right now. Pregnant women are told not to eat any fish. They do. So it is a quandary at this point because we've used mercury for so many years. It's now in the water system. It's now coming up the food chain. So it's sort of like this. Krill have a little bit of mercury because they get the mercury from the water. Then little bit bigger fish eat them, and bigger fish eat them, and bigger fish eat them, and you can watch the amount of mercury going up. Okay, so the bigger fish like halibut and albacore have the most mercury in them. Trout and tuna in a can have a little bit less. Now, if you do trout in a freshwater lake that is not in our freshwater, what am I trying to say, like a river that's constantly flowing and that doesn't have a lot of pollutants upstream, then you're probably better than a trout or a salmon that is coming in from the ocean. Okay, so there's a lot of things to be thinking about here. As far as how do we take mercury out of the system now that we've got it in? Okay, so things to think about. Okay, so let's look at enzymes and clinical diagnosis. As we look at it, amylase, the major diagnostic that we use there is liver and pancreatic disease. We look at amylase and see how much they have, what's going on with it. Prostate cancer, acid phosphates. Liver bone disease, we look at alkaline phosphatase. Muscle disorders, myocardial infractions, creatine and phosphokinases. And you can just go down. Hypertension, renin is often what they're using to diagnose that. So then we get to isoenzymes. I believe this is the last part, if I remember right, or close to the last, which is nice. Okay, so isoenzymes are multiple forms, iso, like isomers, multiple forms of enzymes which differ in physical and chemical properties. They can catalyze the same reaction as an enzyme. Isoenzymes are produced by a single gene, and some may result from more than one gene. Isoenzymes can be separated by heat inactivation, chemical inactivation, or electrophoretic techniques. So we can separate them according to do they like positive or negative kind of stuff. Okay to move forward? I know that I can see pens flying. Okay, we're going to watch another little video. You may